All right, welcome everyone. I'm going to share my screen. All right. So for the first half of lab today, we're doing a review session for our exam, which will be a week from today. And you saw in the introduction to the exam, sort of what the logistics of that are going to be. It is going to be an online exam, so you can take it during a lab time next week if you want, or you can take it during any 2-hour block that you choose between There we go. The end of class on next Wednesday, October 6th, and 15 minutes before the start of class next Friday on October 8th. So to get the full 2 hours, you want to start the exam no later than 10:45 a.m. on Friday, October 8th. You get a 3" by 5" note card. You can use the normal probability table on Canvas if you want. Otherwise, you can also solve those same problems using your calculator or R. You can use a calculator, not Wolfram Alpha, and R. There will be 1 or 2 questions that are going to be multiple choice and auto-graded on Canvas. And then the other questions you'll answer on your own paper and then submit your work to these drop boxes on Canvas, like what we have for the practice exam. So just take the exam, write your work down, and then after you're done with the exam, or after the time is up, whichever comes first, just take photos of your work and then upload them to each question's Dropbox. Are there any questions about sort of the logistics for the exam? All right. So then, what questions do you have about the practice exam problems? Joey.
Number 9.
Number 9. Okay. So a random sample of size n is selected from a gamma distribution with known alpha and unknown beta. So we have this density function for y sub I. Oh, sorry, there was a typo there. Did I get that fixed on the practice exam? So we want to start by finding the method of moments estimator for beta. So the method of moments estimator is the one we talked about yesterday, 2 days ago, by setting the moment of the random variable or the distribution equal to the sample moment. Here we're just trying to estimate one thing. So we just need one equation made out of the first moment and first sample moment. So these sample moments are all the average of y to the k in the sample. So for the first moment, it's just the average value of y to the 1. So that's just y bar. And the first moment of the random variable, the theoretical moment, that's our expected value of y to the first. So that's the mean of y. So using the mean of a gamma distribution, that's alpha times beta. And then we know alpha, we want to find the estimator for beta. So we just need to solve this equation for beta. So we get that the method of moments estimator for beta is y bar over alpha. So then we want to find the maximum likelihood estimator. And here I gave you what the answer is, so you can use that to check your work. But I would not recommend like starting from this answer and trying to work backwards. That would get pretty messy. So to do the maximum likelihood estimator, our strategy is to write down the likelihood of beta, which really just means the probability of the y sub i's as a function of beta. And if we're working with a random sample, we're assuming that those y sub i's are independent. So that means that the likelihood, of beta is, well, we know it's the probability of y sub 1 dot 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 up through y sub n given the value of beta. But if the y sub i's are independent, then this is just the product of the probabilities of the y sub i's. Yeah. And this is by independence. And we saw yesterday that a more concise way of writing this product of probabilities is we could write a repeated product using pi notation. So this is the same thing as sigma notation, but for multiplication instead of addition. Oh, my bad. This was the gamma distribution, which is a continuous random variable. So we should have densities here instead of probabilities. So then we can replace this density function with the density function for the gamma distribution, which we were given in the problem. So that gets us this first version of our likelihood right here. And then our goal is to try to get it out of this pi notation for the repeated product. So for example, anything here that doesn't depend on I, so it doesn't have a y sub I in it, is just being raised to the nth power because we're just multiplying, say, gamma of alpha by itself n times. So that gets us sort of our constant term, 1 over gamma of alpha raised to the n times beta to the n times alpha. Anytime we have a constant being raised to a power that involves the y sub i's, there we can say, well, if we're multiplying e to the stuff times e to some other stuff, then we're going to end up with e to the other plus stuff. So this is applying our principles from high school algebra of working with exponents. It just looks more complicated here because the things in those exponents have subscripts on them. It's e to the negative y sub I over beta. So here we're going to end up with e to the negative sum of the y sub i's over beta. And then this part in the middle, we have y sub I to the alpha minus 1. So what we've got there is y sub 1 to the alpha minus 1 times y sub 2 to the alpha minus 1 times ... So there, we can rewrite that as the product of the y sub i's raised to the alpha minus 1. So that's what this middle part is doing. We've got the product of the y sub i's to the alpha minus 1. And then we're turning that into the product of the y sub i's quantity to the alpha minus 1. Questions so far about this? All right. So then one of our strategies yesterday was that it's often easier to maximize the log likelihood than it is to maximize the likelihood. And that'll give us the same estimator either way. So we're taking the log of our likelihood. And here I just said that this whole thing in front, this 1 over gamma of alpha to the n times beta to the n times alpha. No, this 1 over gamma of alpha to the n. All of that doesn't depend on beta, which isn't what we're trying to estimate. So we know that when we take the derivative with respect to beta, that derivative is just going to be 0. So I just wrote this as the log of a constant that's a function of alpha and n. And I stuck the y sub i's in here. Oh, right, because that's coming from here as well. So let me write this out. Yeah. So we've got our likelihood, and we said that that was one over gamma of alpha raised to the n times 1 over beta to the n alpha times product of the y sub i's raised to the alpha minus 1 times e raised to the negative sum of the y sub i's over beta. Okay. So now we know that our plan is to take the log and take the derivative with respect to beta. But anything in here that doesn't involve a beta, once we take the derivative, it's going to go to 0. So we don't actually care that much about writing out what the log of these pieces is. We can just write this as the log of L is equal to the log of some constant C that is not technically a constant. Technically, it's a function of alpha and n and the y sub i's. Plus the log of these other two pieces that do involve beta. So plus the log of okay, 1 over beta to the n times alpha plus the log of e to the negative sum of the y sub i's over beta. And now we can simplify this sum. Kyle.
Will we have this document to look at later?
Yeah, I can save this and post it on Canvas. The recording will also be posted in the playlist that's on Canvas as well. All right, so we still have this log of a constant that we're not really worried about. We can rewrite the 1 over beta to the n times alpha as beta to the negative n times alpha. And then the log of e raised to a power is just that power. And then when we're taking the log of something with an exponent, we can bring the exponent down outside of the log. So we get negative n times alpha times the log of beta. Kyle.
Why do you denote them as logs and not natural logs?
That's a convention, sort of as you transition from high school math to grad school math. Log becomes by convention the natural log. It would also be perfectly acceptable to write it as ln, but by default in this class, if you happen to see a problem that says take the log of this, that means the natural log unless it specifies otherwise. All right, so then that brings us to this point. We've taken the log, then we take the derivative with respect to beta. So the log of the constant goes to 0. So we have negative n times alpha over beta, because the log of beta is 1 over beta when you take the derivative. Then we have the log of the negative sum of y sub i's over beta. So treating that beta as beta to the negative 1. We bring the negative 1 down in front, so it'll cancel with this minus sign, so we get plus the sum of the y sub i's over beta squared. And we're setting that equal to 0 so we can find the critical points. And from there, so we're trying to get beta by itself. So get the n times alpha over beta on the other side of the equation. Multiply both sides by beta. Multiply both sides by beta again. So we end up with beta hat is equal to the sum of the y sub i's over n times alpha, which we can simplify to the sum of the y sub i's over n is just y bar. So we have y bar over alpha. Questions about that? Vivian, questions? All right. So then we're checking whether the maximum likelihood estimator is unbiased. Helpful hint, notice that even if you were not successful in doing part B, you could still do part C by using the maximum likelihood estimator that I gave you. So to check whether it's unbiased, that means we want to check whether its expected value is equal to the thing we're trying to estimate. So we have the expected value of y bar over alpha. We can pull the 1 over alpha outside of expected value. The expected value of y bar is equal to the expected value of y. Be sure that if you needed to, you could sketch a proof of that. In a problem like this, I don't expect it, but in a problem that explicitly asks you to prove that, then you might need to. We already used the fact that the expected value of y sub I from a gamma distribution was alpha times beta. So here we have 1 over alpha times beta. So that's equal to beta. So that proves that our maximum likelihood estimator of beta is unbiased. And then what is its mean squared error? Typically, it's easier to use the formula for mean squared error, that it's the variance plus the square of the bias. And we already found that this was an unbiased estimator, so the bias is 0. So we just need to find the variance of the estimator, so the variance of y bar over alpha. So we can pull the 1 over alpha out. Remember, when you pull constants out of variance, they get squared. So we have 1 over alpha squared times the variance of y bar. The variance of y bar is equal to the variance of 1 of the y sub i's divided by n. Does anybody want to go through a quick proof of that? Should we do that? So prove that the variance of y bar is equal to the variance of y sub I over n. And this is assuming that the y sub i's are independent and identically distributed. So this proof is not specific to the gamma distribution. It works in general, but we do need the y sub i's to all have the same variance, and we need them to be independent. All right, so let's start with writing out what y bar equals. So that's 1 over n times the sum of the y sub i's. All right, what can we do with that constant 1 over n? Kyle,
Pull it out and square it.
pull it out and square it. Times the variance of the sum of the y sub i's. All right, let's go ahead and use the table method. So we've got y sub 1, y sub 2, dot, dot, dot. So y sub n. And similarly along the rows. All right. So in the boxes in this table, we're filling in either the variance if it's in the row and column of the same variable, or the covariance if the row and column are not the same variable. So for the variance of y sub 1, that's just the variance of y sub 1. And here we're assuming that the y sub i's have the same distribution. So that means they have the same variance. So I'm not going to make this specific to the variance of y sub 1. I'm just going to leave it as the variance of y sub I. Same thing for the variance of y sub 2. Dot, dot, dot. And the variance of y sub n. So we're going to end up with every value on the diagonal here is the variance of y sub I. So we have n copies of the variance of y sub I in this table. What should I fill in here for the covariance of y sub 1 and y sub 2? 0, because we assumed that the y sub i's were independent. Their covariance is going to be 0. So that means that everywhere on this table, other than the diagonal, we're going to have zeros. So the total variance of the sum of the y sub i's is going to be the sum of the entries in the table. And we said that that was the sum of n copies of the variance of y sub I. So n times the variance of y sub I. So now we have the variance of y bar. Is 1 over n squared times the variance of the sum of the y sub i's. Well, the variance of the sum of the y sub i's is n times the variance of y sub I. So now we can cancel one of these n's, and we're left with the variance of the y sub i's divided by n. Questions about that? All right. So we want the variance of y bar over alpha was our estimator. So that was 1 over alpha squared times the variance of y sub I over n. And then we can use facts about the gamma distribution to write in what that variance of the y sub i's is. So that is alpha times beta squared. So we have 1 over alpha squared times alpha beta squared over n. So that is beta squared over alpha times n. Is our mean squared error for this estimator. Questions about that? All right. Parts D and E are talking about consistent estimators, which we'll talk about in class tomorrow. And then suppose that alpha equal to 2 is known, and you observe these sample data, so 3 observations. Find the value of the maximum likelihood estimator. So that's just, can you apply this formula that you found for the maximum likelihood estimator? So take y bar, the average of these 3 numbers. So add them up, divide by 3, you end up with 126, and divide by the value of alpha. And yep, that's it for question 9. Questions about that question 9? Kyle.
So for 9C, when it asks if it's unbiased, we would say no, because the biasness equals 0.
You'd say yes, because the biasness equals 0. And the reason that equals 0 is because the expected value of the estimator equals the thing we're trying to estimate.
Yep.
All right. Other questions about the practice exam? Sam.
Just kind of a general question, but why didn't we use that like product notation with the Bernoulli distribution? Like, how do we know we use this sort of product notation?
Good question. So actually, I'll show you my notes about that. I actually did initially use the product notation for the Bernoulli distribution. Problem when I was making my notes about this. But I just figured it was the first time you were seeing maximum likelihood. So I figured I'd wait until the second problem to introduce that, because the Bernoulli distribution is sort of simple enough that you can understand what the likelihood is going to be without necessarily needing the product notation. These ones with subscripts, that's an indicator variable, also known as a dummy variable. So that's the same thing as we talked about briefly yesterday with an I with a subscript. So I, there, all right. Subscript, say y sub I equals 1. This is a variable to indicate whether the thing in the subscript is true. So this equals 1 if y sub I equals 1 and 0 otherwise. So you can also write this as a 1 with a subscript. Other questions about the practice exam or other material we've covered so far this semester? Maria?
Can we go through the maximum likelihood estimated for 10?
For number 10, yeah. Okay, so this was a Poisson distribution, and it's giving us the density function and expected value and variance. All right, so the first step in the maximum likelihood estimator is to write out the likelihood. What's that parameter in this problem? Lambda. All right, so again, we'll start by using the pi notation for the repeated product. And then we'll use the density function that we were given in the problem. So this is f of x sub I. So e to the negative lambda, oops, forgot the negative in there, times lambda to the x, sub I, nope. Divided by x factorial. And then we want to take the log of this. Oh, actually, before we take the log, let's simplify it some, get it somewhat out of the pi notation. All right, let's see. So in our numerator here, we've got e to the negative lambda. Oh, this should be x sub I, sorry. E to the negative lambda does depend on lambda, so we do care about it because its derivative is not going to end up being 0. But it doesn't depend on I. So as far as this product is concerned, this is just a constant. This is just like 3 times 3 times 3 times 3. Except with e to the negative lambda instead of 3. So we're going to have e to the negative n times lambda, n copies of that, times lambda to the x sub i's. So this is the same situation that we talked about up here, where we have a constant raised to the power of some stuff times the same constant raised to the power of some other stuff. So that repeated product is just becoming lambda to the sum of the x sub i's. And then we're dividing by the repeated product of these x sub i's. So we can push that product notation into the denominator here. So we have the product of the x sub i's factorial. All right. So now we're ready to take the log likelihood. So taking the log of what we just found. So the multiplication is going to turn into addition. So we're going to have the log of e to the negative n lambda plus the log of lambda to the sum of the x sub i's and then if multiplication is turning into addition, then division is turning into subtraction. So minus the log of the product of the x sub i's factorial. And we can simplify this sum. So the log of e to the negative n times lambda is just going to be negative n times lambda. And the log of lambda to the sum of the x sub i's is going to become the sum of the x sub i's times the log of lambda. And I'm not going to bother simplifying this log of the product of the x sub i's factorial, because again, all we care about is maximizing this with respect to lambda. So we're going to take the derivative with respect to lambda. So we know that this log of this thing that doesn't involve lambda, the derivative of that is going to be 0. So we don't really need to simplify it at all. So the derivative of the log with respect to lambda. Let's see, negative n times lambda. Derivative of that is just going to be negative n. Plus, oh, maybe I should use parentheses here to be more clear. That here it's just the x sub i's that are inside the sum, not the log. We could pull the log out because it doesn't depend on I, but this is sort of the way it started with was we were pulling down the sum of the x of i's outside of the log to begin with. So here we have the log of lambda. What's the derivative of that?
Over lambda.
1 over lambda. So we're going to have our constant divided by lambda. And I will clean up my notation here. That's I goes from 1 to n, like that. Questions so far? All right. So that brings us to this point. We're setting the derivative equal to 0. And then we want to solve that for lambda. So add n to both sides of the equation. We have the sum of the x of i's over lambda equals n. Multiply both sides by lambda and divide by n. So we have the sum of the x of i's over n equals lambda. So lambda, our maximum likelihood estimator of lambda, is x bar. What would you do if the problem asked you to show that this critical point was actually a maximum? Davis.
What's second derivative test?
Yeah, we take the second derivative. So we're taking the derivative of our derivative of the log. So negative n now does not depend on lambda, so its derivative is just 0. And here we have a constant, the sum of the x of i's, times 1 over lambda. So times lambda to the negative 1. So the derivative of that is going to be negative lambda to the negative 2 times its constant. So then, depending on the problem, we might need to plug in our estimate for lambda. So we might need to plug in x bar or the sum of the x of i's over n. But in this case, we can see that we've got lambda squared, so that's going to be positive. The x of i's from a Poisson distribution are all positive, or all, sorry, non-negative whole numbers. So 0, 1, 2, 3, dot, dot, dot. So their sum is also going to be positive. So we've got a negative times a positive times a positive. So this is always less than 0. So that's telling us that the function, the log likelihood, is concave down. So the critical point we found is a maximum. Questions about this one?
have to show the maximum? Oh, wait, never mind.
Yeah, this problem didn't say, remember to show that it actually maximizes. So in this case, you don't have to show that. So the other way you could do this, besides using the second derivative test, would be the first derivative test. So that would be draw out a number line with the maximum value that we found, so the critical point that we found, the X bar, and test a point on each side of it, plug those into the first derivative, and you want to see that on the left, the first derivative is positive, and on the right, the first derivative is negative. So the function log likelihood is increasing and then decreasing. But I think the second derivative test usually ends up being easier because you only need to plug in one point and you're sort of, you know that the point that you're plugging in is a convenient point versus trying to plug in something that's on either side of X bar can be tricky to find a good point when you don't actually know what X bar is, when you're just representing it as a variable. Other questions about the practice exam or other material that we've covered this semester? Sam?
Can you like quickly go over how you apply the code to those graphs?
Sure. Okay, so this was our code. And the goal with this sort of problem is to try to connect the code with one of our distributions based on the normal distribution. So here, we're taking numbers from a normal distribution in samples of size 5 and taking the variance of each sample. So that's giving us S squared is the sample variance. And then the my out value is 4 times S squared divided by 9. And so let's think about which of our distributions based on the normal distribution we know that use S squared. Okay.
Doesn't F distribution use it?
The F distribution uses an S squared. The F distribution actually uses 2 S squared. So like S1 squared and S2 squared. So that could be it, but in this case, we just have one sample. So is there another distribution that uses an S squared from just one sample? Joey?
Is it T?
So the T distribution would give us n minus 1. No, what am I doing? Bar y minus mu over S over the square root of n. That would be a T distribution. So if it were just S, the sample standard deviation, then we would be looking to make it into a t-distribution. But that doesn't quite fit with what we have in this problem. First of all, because we have the variance, not the standard deviation. And second of all, because the thing involving S that we computed is in the numerator here. And for the t-distribution, we would want it to be in the denominator. So what is left if it's not F and it's not T? Chi-squared. And what function of S squared has a chi-squared distribution?
N-1 times S squared over sigma squared.
Yeah. That has a chi-squared distribution with n-1 degrees of freedom. So now let's go back and compare this with the code. That we have our S squared is our X, times 4. Yeah, that's 1 less than the sample size. So that's n-1. Divided by 9, that's the square of 3. So that's the square of the population standard deviation. So in other words, that's the population variance, sigma squared. So that's telling us that my out has a chi-squared distribution. The general shape of the chi-squared distribution is that it covers values 0 and larger, and it's right skewed. So that lets us, oops. Rule out 2 of the graphs. So it can't be graph B or D. It can't be graph D because that's a symmetric graph, not right skewed. And it can't be graph B, both because it's a symmetric graph and because it has values less than 0 here. So it has to be one of graph A or C. And to decide which one, then we can use the degrees of freedom. So the mean of a chi-squared distribution is its degrees of freedom. So we expect a mean of about 4. So on this graph A, we've got 0 and 5. So yeah, a mean of around 4 looks about right. On graph C, this is 0, 10, and 20. So it looks like the mean here is about 12 or so. So that's too large. Questions about this? Other questions about the practice exam or material from this course? All right, so in that case, let's transition to our lab for today. So this is going to introduce you to the idea of consistency, which we'll talk about more in class tomorrow. So please go ahead and open up Lab D. Give it a try and let me know when you have questions.
It just takes so long. And then they'll pop up. 20 seconds.
Okay. Is that one better?
Yeah.
Okay.
Why are you on the word? Like, why are you doing I'm gonna be so mad. It didn't like point on. Gosh dang it. Yeah, I don't know. It did 0.5 one time and it gave me a mean of 8.
Are you sure you're gonna do it?
Yeah.
Where did you define monitoring?
I could have maybe like not loaded it. And I loaded it.
Yeah.
I don't know.
So I'm warming up slowly into black. Yes. Vivian, any questions so far?
Way too many times.
All right.
And see.
If you want to, go for it.
NC's the call.
We want columns.
What?
Oh, good, you got it. Sorry.
Wi-Fi.
Yeah, well, it's a very. Okay. Wait, actually, it does. One new column.
Correct.
Unless that's.
Yeah, that's why I included the check that the mean is actually close to 50.
Is it implied that you want a whole new column or just want to compute each row's mean?
So you want to store each row's mean in a vector, so you have a vector with one value from each of the rows.
So we could either
You
make
can
it
choose
a
whether-
column or just make a row.
Yeah, you can choose whether you want that to be a column and a data frame or just a standalone vector.
Well, make a decision because work.
not in the spirit of the teamwork on this lab.
I'm just being honest.
We did some work.
Well, you got great teamwork, but I'm not pulling weight.
You find all the spelling mistakes.
Wipe off the dust.
I figured it out.
All right, let's make it a comment.
Oh, no, I didn't remember.
I feel better about doing this. Let's emphasize silence back there.
Here we go. Is this just making it happen?
That's the friction that you need to get through in order to get to the actual.
It's just a little while.
Should I delete the code?
No.
Oh, well, I just did.
Oh, single sound.
So we don't need to do formula on this one?
No.
Okay.
Well, we think we did it. We don't have any way of confirming. It's not just-
That's what we did.
Yeah. All right. Yeah.
Minus some,
But I was just wondering.
This-
Oh, that's what you deleted?
Yeah.
so we're trying to see.
So we just do. as normal.
I forgot the L in it.
Two,
This is a formula there, right?
So it's called. The minimum.
Oh, yeah. there's a few minimum hours.
It's confused,
Road
like,
use.
test the people,
We used to 2 times.
but then I think we have other means that we just did.
This might be actually what we should. Examples of five. Minimum.
We have population.
Just put the minimum.
Size five, but it does take the minimum of the row means that we have. That makes sense. We don't need it, so can you click that in the back?
What does Y bar represent?
So we just have to be neutral.
That's not good too.
So row means will never be the minimum of any of these rows. We're just wondering because we chose to make a brand new vector to put the means in.
Great.
So we're wondering, if this is finding the minimum of each row, the sample size matrix. So that's excluding the means that we found.
Correct, because you did not put any.
Yeah.
Use similar thing,
Is that a problem?
No, that is good,
All right.
because these are 2 separate estimators that we want to compare.
Yeah, I just didn't know where it was going.
Roman.
So here is for each row of the matrix.
Is N 10,000?
Oh, we had two. Better. So that was Romeo.
Five was possible. Right,
no.
5 times 1.
And is it five?
I think I just like picked the number 2 for some reason.
Is it two?
Any questions?
Alright.
No,
Well, I mean, we do that. Eight, but it's like that, right? It's fine.
So that's saying apply the win function.
Yeah.
It's going to every row of the sample size, right? And the one is saying with every row. You got a 2 there, but it's saying it's going to
Oh,
Yo.
oh, yeah.
oh, so which one? I've heard of it. 3.
Yeah, so this is a task.
Any questions so far, Vivian? All right, carry on.
This is just a kind of question.
Mhm.
I thought you had to do 2 ands and 2 bars.
There's also a 2 ands and 2 bars. And
Do those mean
I-
the same thing?
there is a very slight difference between them that I can never remember.
All right.
So in practice, I always start by doing 1 and then see if it does what I want. And if it doesn't, then I go back and play in the second one.
All right.
Yeah.
Wait. This is wrong. Wait, never mind. I think it's the wrong line.
So this already calculated.
No, wait, no, you just go all of it.
Oh, yeah.
No, no. Here, for the portions.
The minimum of. Sorry, what's my?
Well, so this is, these are the ones.
So these
That
ones
represents
sounds
it.
fine.
Yep. So you don't need row names here.
It's kind of the same questions.
No, before you were taking a mean at each row.
Do some.
Here, you
uh,
found my mins that
data
the
one.
minimum of each row, and you just need to multiply that by 5.
Two.
Okay.
Yeah.
A line bar, but
Yeah, so that's the error message you were getting was, you're telling me to take the mean of a row, but
Try
I
to find
only see
7.4.
one vector here that doesn't
Try to
have
find
rows.
those portions of samples. So
yeah, okay.
this would just count on, and then we just divide this by n. And also that's a proportion. Is that an absolute value function?
ADS.
ABS, okay.
manage like a new data from that was big and then nice to and then use that council ones. From that,
Yeah, just do a count.
you could just pick those.
Yeah, you just
Yeah.
did that, yeah.
From that between 2.4 and 2.6.
That's still, they don't want to be good too. Or
One to the control bar. I think I found something like those endpoints there. And you can find out,
Oh.
Hey Vivian, let's see, REXP 50,000, 1/2, looks good. So making a matrix of that with 5 columns looks good. Yeah, so using apply to apply the mean to each row. And then beta 2 equals 5 times my mins. Yeah, looks great. You're welcome. There is just one beta. Beta hat 1 is the first estimator and beta hat 2 is the second estimator.
basically two. Always be with it.
Looking at this, I'm seeing number 1:5, so that's 5 values.
Yeah.
It should be 10,000 values.
Cool.
So I think you might have gotten a matrix transpose somewhere.
2+.4, 2
Oh, right, this is probably supposed to be 5.
Yes.
We did 10,000 rows, so we made
Yeah.
10,000.
So you made 5 samples of size 10,000 rather than 10,000 samples of size 5.
Yeah.
Yes.
Yeah.
Any questions?
Sorry, where you go?
Yeah, that looks good.
Oh, wow, too.
And then gotta do the same thing. Switch out the beta one for Google Center.
And we, okay, see, now it's giving me a number that's not just 100.
Any questions?
There we go.
So I don't know.
No, you really, yeah.
So I'm just
So,
taking the sound. Absolutely.
yeah, I was in the beta one, that's already, beta one over here. And then minus, well, you can do beta, you shouldn't do beta two, because we're not looking for beta two, we're looking for the minus the trip, which is just two.
And then I'll design that.
10,000, but the first you're gonna want us to do less than say the 0.4, because we want to make
You could also do
that.
roaming, but that works just as well.
So basically, it's doing beta one minus two, and it says, hey, that's less than 0.4, count one. If that's not less than 0.4, so it's 0. So it adds up all those ones. So we're back by the 10,000 times, it did that,
Just like mentioned before, you do it for roll.
giving us the proportion.
So you can use that.
A bit different than But definitely good.
Almost never do the same thing. It's big, it's fine, right?
Yeah. Look at that.
All of these.
Yeah, R does element wise.
Cool, that was closer.
So
Supposedly we're going to
a vector times 5 times 5 times 2 times.
The first one.
So you're gonna want to store that in a vector.
Because the proportion amount of times that it was closer to the true mean. Yeah.
Any questions? Hey, Vivian. For part C, is it 1.6 is less than beta 1 and beta 1 is less than 2.4? Yep. So taking the sum of that would add up all the trues as ones. So to tell you how many beta 1s satisfy that.
Oh, wait, I should just add there.
So let me check on something. Yeah, so I was just checking if it made any difference whether you do 1.6 is less than beta 1 or beta 1 is greater than 1.6, and it doesn't.
We don't know what we're generating samples of.
From the same distribution as in part A.
Okay. Now. Okay.
Any questions? Cool.
Be both my chest. Yes. Let's see this one. Yeah, we got it. Oh. Yeah. Because we-
They. Turned out good.
So, we still- yeah, we still want- Hopefully the one that-
It was so much better than mine.
Did you make a
But I'm not-
new-
Did
the one function?
the same, so I'm just like,
Did you make it different than the one?
No, I thought it was just, I was just. real, but we're both not.
so we generate that. So that's asking the people finance figures, that's it. It's not big, as I did earlier.
Mhm.
And
So beta one, Romans, and beta two, what are we doing?
Change to that.
Oh.
Yeah, basically.
And
Oh, that was last one.
It just seems like
where did I?
Correct. You divide by the number of samples that we take.
One is 98, but the other one is 18.
Yeah, why not find my stuff by the right thing? Oh, wait, I'm not. Where did I go? That's how-
Cool. So what did you find?
Here's 500.
Or was I supposed to?
We're supposed to be 10,000. That's the amount.
Exactly.
Well, wait, we're generating 10,000 of sample sizes.
How's it going?
And those are,
Well, yeah,
and that close.
yeah, but it's. We're generating 50,000. Five, so that would give us 10 back. And that would be our first.
Some of those teacher things.
Yeah, I know.
Those are the-
It's-
How's it going?
Good.
Okay, should be 500.
Is that?
You're right, with 100.
Well, because.
Like, yeah, that's not why. It's because.
So we expect those numbers to change slightly when you
Generate 10,000
generate
samples.
the
And then we
numbers.
made, then we put those, we put 100 samples in each row. That's it, giving us 100 rows. So that's why it's 100, or you're right.
How many random numbers are you generating? How many do you want to generate? Not 10,000 random samples. But how many values should be in each random sample? How many random values should be in each random sample? Part B.
So you don't-
No, see, 10,000 times 100 numbers.
Oh. So it's the same sort of thing, like generate 10,000. Or sample size of 5 for there.
Right.
So,
Put that in here.
so yeah,
So-
what do we?
So how many samples do you have and how big was each sample?
Oh, so we have to multiply that by here too. So
I already
50,000.
did that for you up there.
Yeah,
So in part A,
they're supposed to be.
it told you to generate 50,000 random numbers.
Yeah.
And then you put those into 10,000 samples of size 5 each.
Got it, okay, okay. All right, so this is not. close.
Yep. So you're gonna want 100 columns. Not 100 rows. It's not different. Before you did 10,000 rows, so that gives you 10,000 samples.
What?
Samples.
Oh.
Observations, or 5 columns.
Oh, I think it's.
I mean, it's about the same. This is supposed to be about the
So you
same.
can specify that either by number of rows equal to the number of different samples you want, or number of columns equals the size of one sample.
Oh, I checked it.
Yes. That needs to be the total number of random observations you want, what's the number of samples times the size of it.
One isn't the consistent.
Like we're taking whatever we're doing. Column.
So what we want is one row to be one sample. So you can either do n row equals 10,000,
Yeah.
or you can do n call equals 100.
So.
Double check what your variable is called. Beta one. Mhm.
And then so this would it be also over all the samples?
No, because now that sum is giving you, it's counting one for each row where that was stored. So that should be divided by the number of rows.
Yeah.
Yeah. Oh, what's your end?
Oh, yeah.
Yeah. That was my. Any questions?
So,
Cool. So what'd you find?
That beta one. It's not consistent, but it gets more accurate, but beta two is consistent, but not really accurate.
What does it mean to be consistent?
It's like the proportion of how good it is the same.
No,
Oh, did I mess them up?
you mixed them up.
Oh, I hate that they're the same words that mean the same thing.
Yes, the idea is we say that the estimator is consistent if it consistently gets better as you increase the sample size.
okay. Well, there's one that was really bad, and the other one increased. So then, there's both. There's one more consistent than the other.
So we have pretty convincing evidence that beta one is consistent. For beta two, if you ran it multiple times, sometimes you'd see it increases and sometimes it decreases.
Okay,
And we're gonna prove tomorrow that it's actually not consistent.
so we say it stays the same, or should we use whichever one? What happened in ours?
I think stays about the same as reasonable.
Consistency is as the sample size gets larger, it's more on point.
Yep, it gets more likely to be close to the thing you're trying to
And
estimate.
accuracy
But
just
how
means
about,
you're really
yeah,
picking this
yeah.
one spot, it's not the right spot though.
No, that's precision.
What's she saying?
Accuracy is
Yeah,
on
some-
average, you get the correct value.
Okay.
Yeah,
So there's a question on.
Consistency, accuracy.
So are beta two
Okay, so beta one
for
is
the first
consistent.
problem
Yes.
was really low. I mean, it's increased significantly.
What did mean the same? It's like.
Is this one look right? This one.
It's just because the naming
what
of
are you
the
dividing by?
thing is just ridiculous.
You want to divide them by the number of samples.
Rows.
Yeah, the number of rows.
Oh, so we're.
That's what I was like, that's not right, it's just 1,000 samples.
Right, but what we're counting here is for this row was beta two
I want to
close
say it's not
to.
more accurate. I thought it
Beta.
No, you just gotta avoid those words now.
It didn't get
Right, because
more.
beta two is
I'm
a
just
number
saying
of
it isn't
computers in a row.
consistent because that's
And
the
so we're
sample
counting how
size
many
increase, the
computers.
proportion of the success did not.
1.6 to 2.
Okay,
Because I want to say I got.
then,
Yeah.
Yeah.
Now we see it.
one
Definitely.
thing. Okay.
Any questions?
Yeah. I think that's what this is called. So like this one, it's the.
That's tricky.
I know, why is there, I thought there were just 2 words and now there's 3.
No, so you want.
There's consistency, accuracy, and precision.
That as the sample size increase, the proportion captured.
That's consistent. Consistent means the sample size is
No, sorry,
it gets better.
I didn't
Since
realize
as
that
the
was
sample size
unclear.
increases,
No,
the
no.
proportion got bigger.
And precision means. Then if I were.
So how many random numbers do you want?
What?
I didn't even. I didn't-
Yeah, so I would start with.
Do you cover over this 10,000?
Oh.
We just. skipped that.
Oh, no.
Oh, you skipped them?
What's the rate?
Precision means it varies.
Want the
It's the
comma.
same spot
I hate that.
every time, but it's not the right spot, probably.
And I think we're close to.
Specify how many columns.
No.
Accurate both.
What is accurate?
Consistency, precision.
Accurate, okay,
Oh, yeah.
accurate means. I don't know. My-
what I heard is like average is close to the target.
Yeah,
Yeah, precision is like the, all the things that the same.
Yeah.
but not.
Accurate means that it evens out instead of target.
That's still excellent.
Yeah, same. I'd seen that way back too, and I was like, yep.
Not
that's
use
about
that.
And didn't it pay off? The
Hey, Vivian.
portion rate, the portion rate.
So REXP.
Okay.
So this looks good, except how many random numbers do you want to be generating when you do REXP?
Yeah.
How many did we do in part A?
You don't have to explain why, right? It just has these things, this is a couple sign, right? I'm gonna say, yeah, I think. it is.
How many total random numbers did we generate from REXP up in part A? $50,000. Why did we generate 50,000?
So, this is what's gonna happen.
Right, but that was because we wanted to put them into a matrix that would represent 10,000 samples, where each sample had 5 observations in it. So 10,000 times 5. See ya. That's what we did for part A. For part C, right, or part D, sorry. The number of random numbers we want is going to be the number of samples, 10,000, times the sample size, the number of data points we want in each sample. So 10,000 times 100.
Not that it's like, or I guess a lot to cover, but it's just like.
Don't say that.
I'll be right back, Vivian.
We're just
I don't know if we could just submission box on the assignment fill out.
Sorry about that. I will fix that.
Thanks.
I will not remember after today, so.
I just got told that there's no submission box on the lab, so I'm going to fix that.
Oh, well, actually, that's not pretty good. Oh, really?
Wait, so there's no coding for this test?
Correct. The most you might see is, here's some code, interpret it, or say what the error is. All right, that should be fixed now.
Is there actually 10 questions?
I don't know how many questions there are going to be. I think
Oh,
the practice exam is a relatively good representation of the length.
that's so long.
You get 2 hours for it. So yeah, but the reason why 50,000 is the total number of observations is because we wanted to get 10,000 samples of size 5 each.
Oh, yeah, I got you.
Cool.
Oh,
All right. So I should get going because I have another class at 3 o'clock. But feel free to email me if you have further questions about this. You're welcome.
What, Dorothy?
You too.
Oh,
Bye.
okay.